Hello students, in the last class we have studied the article countable and uncountable sets. In that article we have studied some important definitions and some results. We have defined the infinite set. Then we have defined a countably infinite set. Also we have seen some examples of countably infinite set. After that we have defined the countable set, then the uncountable set. Also, we have seen some results about the countable and uncountable sets. After that, we have proved some results about the countable and uncountable sets. We have studied results such as the countable union of countable sets is countable. Then, a subset of countable set is countable. Then, finite product of countable sets is countable. And similar results we have studied. Now in the today's class we are going to study the next article, which is the well-ordered sets. So let us begin with this article. So before going to actual definition of the well-ordered set, where this concept has originated, that we'll see. We know that one useful property of the set of positive integers, that is z plus, is known to us, and that property is that each of the non-empty subset of z plus has a smallest element. Consider any non-empty subset of z plus, then definitely it has the smallest element. So this property we are going to generalize, and this is the base of the well-ordered set. So let us begin with the definition. Definition of the well-ordered set is a set A with an order relation less than is said to be well-ordered if every non-empty subset of A has a smallest element. If A is a set which has an order relation denoted by less than on it, then that set A is said to be well ordered if its every non-empty subset has smallest element. For example, we'll consider examples. So first example, consider the set. Set consists Cartesian product of the two sets. The first set is the set consisting of only two members 1 and 2. And second set is the z plus, which is the set of positive integers. So consider the set, this Cartesian product of these two sets, in the dictionary ordering. Then if we arrange the elements of this Cartesian product set systematically, then it can be represented as one infinite sequence followed by another infinite sequence, such that the first sequence is a1, a2, a3, continued. Then the second sequence is b1, b2, b3, continued. What a1, a2, a3 and b1, b2, b3 represents here? So that I will mention here. Here a1 denotes the ordered pair 1, 1. a2 denotes the ordered pair 1, 2. a3 denotes the ordered pair 1, 3. And continued in this manner. So obviously continuing in this manner, an will denote the ordered pair 1, n, where n can be any positive integer. Okay, and similarly we have the b1, b2. b1 denotes the ordered pair 2, 1. b2 denotes the ordered pair 2, 2. b3 denotes the ordered pair 2, 3 and continued in this way. So like such are the elements of this sequence. Then obviously if we consider the dictionary ordering, then definitely a1 is less than a2. Why? Because in the a1, 1 is equal to 1, but the second element 1 is less than 2. Therefore a1 is less than a2. Next, a2 is less than a3. As in a2 and a3, the first component is said 1, 1. But the second component of a2 is 2, which is less than the second component of a3, which is 3, and so on. Similarly, b1 is less than b2, as in b1 and b2, first components are same, which are 2, but the second component of b1 is 1, which is less than the second component of b2, which is 2. Similarly, b2 is less than b3, and so on in the dictionary ordering. Also, each and every element of the sequence a1, a2, a3 is less than each and every element of the sequence B1, B2, B3 and so on. For instance, if we consider the A2, then A2 is less than B1. Why A2 is less than B1? Because in the dictionary ordering, first we compare the first component. So first component of A2 is 1, which is less than the first component of B1, which is 2. So therefore, obviously A1 is less than each and every member A1, A2, A3 and so on, as well as B1, B2, B3 and so on. Similarly, A2 is less than A3, A4 so on, as well as B1, B2, B3 and so on. So in this order, each element is less than the every element which falls to the right side of it. Okay, so with the understanding that each element is less than every element to the right of it, it is not difficult to see that every non-empty subset C of this ordered set has a smallest element. Now if we take any non-empty subset C of this one sequence, then it has the smallest element. Why it will have the smallest element? The reason is given here. Because if C contains at least one element from the AN, okay, if C contains at least one element from A1, A2, A3 and so on, then whichever is least among them, or whichever is to the leftmost among them all AI, will be the smallest element of that set C. Next, and if C do not contains any element from the A1, A2, A3 and so on, then definitely it will contain only B's, means B1, B2, B3 and so on. Then whichever is leftmost among them will be the smallest element of the set C. So definitely set, which is the Cartesian product of set containing 1, 2 with the Z plus, that is the set of positive integers, is well ordered, as it's every non-empty subset has the smallest element. Therefore this set is a well ordered set. Next, now consider the second example. Consider the set Z plus cross Z plus, again in the dictionary order. Here also we will arrange the elements systematically as an infinite sequence of infinite sequences. Infinite sequence of infinite sequences. So, and we will show that it is well ordered. Next, let X be a non-empty subset of Z plus cross Z plus. Let A be a subset of Z plus consisting of all first coordinates of elements of X. Then A has the smallest element. Suppose the smallest element of the set A is A0. Then the collection which is the set consisting of all elements B which are such that A0 cross B belongs to X. Then this collection is a non-empty subset of Z plus. Then this collection is a non-empty subset of Z plus. And let B0 be the smallest element of this set, of this collection. Then by definition of the dictionary ordering, definitely A0 cross B0 is the smallest element of X. By the definition of dictionary order, A0 cross B0 will be the smallest element of the set X, and which is explained here by drawing a diagram. So see here, suppose A0 is the smallest element among all A. Okay, A0 is the smallest element and it is here suppose. And B0 is the smallest element among all B. Then A0 cross B0 will be the smallest element. Here it is B0 and here it is A. So A0 cross B0, this will be the smallest element of this set X. Okay, so like such it is shown by drawing a diagram. Next one, consider the third example. The set of integers is not well ordered in the usual order. If you consider the set of all integers with the usual ordering, then it is not well ordered. Why it is not well ordered? Reason is given here. Because the subset consisting of the negative integers has no smallest element. If we consider the non-empty subset of the set of all integers, such as that non-empty subset is the set of all negative integers, then definitely we know that that set of negative integers do not have the smallest element. Therefore, here the condition of becoming the well-ordered set fails. Therefore, the set of all integers is not well ordered in the usual order. Okay. Next, the set of real numbers in the interval 0 to 1 is not well ordered. If we consider the set of all real numbers lying between 0 and 1, then it is also not well ordered, because if we consider the subset of this set, which consists of those elements x which satisfy that 0 is less than x is less than 1, then obviously this set do not have the smallest element. Definitely such subset we have considered, then it is bounded below by 0, but its smallest element cannot be said as a fixed as some one element. Okay. So next one, there are some ways of constructing the well ordered sets. Out of this, two important we are going to study. The first one is that if A is a well ordered set, then any subset of A is a well ordered in the restricted order relation. Means subset of a well ordered set is well ordered in the restricted order relation. And the second way is that if A and B are well ordered sets, then their Cartesian product A cross B is also well ordered in the dictionary order. Okay. So these are the two main ways of constructing the well ordered sets. Now we'll prove the theorem number 10.1. The statement of this theorem is every non-empty finite ordered set has the order type of a section 1 to up to n of Z plus, and therefore it is well ordered. So what we have to show that? We have to show that every non-empty finite ordered set is of the order type of a section 1, 2, 3 up to n of Z plus, and therefore it is well ordered. This we are going to prove here. So let us prove this. First of all, we observe that every finite ordered set A has a largest element. Okay. If we consider any finite ordered set A, then it has a largest element. Next, if A has one element, then obviously it has the largest element. If A is a singleton set, means if it has only one element, then it has the largest element, and it is the same element which is present in that set. Next, we are going to prove this one by the method of induction. So therefore, we suppose that it is true, means this statement is true for all sets having n-1 elements. We are using the mathematical induction here. So we suppose that the statement is true for all sets which have n-1 elements. Next, and let A have n elements, means set A has one element more than the set having n-1 elements, and let A not belong to the set A. Then definitely the set A minus singleton A naught has the largest element. Why? Because we have supposed it as per our supposition state of the mathematical induction. So therefore the set A minus singleton A naught, this consists of the n-1 elements, and as per our supposition it has the largest element, and suppose its largest element is A1. Okay. So suppose the largest element of the set A minus singleton A naught is A1. Then the set, which set A naught, then the set A will have the largest element, and which will be the larger among the two elements A naught and A1. Okay. So definitely in that case set A has the largest element, and it will be one of the two elements A naught or A1, depending on whichever is the larger. Next one. Now we show that there is an order preserving bijection of set A with the set 1, 2 up to n for some positive integer n. Next, if A has one element, if set A has only one element, then definitely there is a bijective correspondence which preserves the order. Next, suppose that this statement is true for all the sets having the n-1 elements, and let small b be the largest element of the set A. Then by our hypothesis, there is a order preserving bijection from the set A minus singleton B with the set 1, 2 up to n minus 1, because we have supposed in the second step of the mathematical induction that for every set having the n minus 1 elements, this statement is true. So therefore, if A has the n elements, then definitely A minus singleton B, this is the set which has the n minus 1 elements, and therefore by our assumption there exists a order preserving bijection from the set A minus singleton B with the set containing n minus 1 elements, and that set is suppose 1, 2 up to n minus 1. And let us denote this order preserving bijection by f dash. So f dash is the order preserving bijection between the sets A minus singleton B and the set 1, 2 up to n minus 1. Next, now by using this order preserving bijection, we will define a order preserving bijection as such. So we define an order preserving bijection f from the set A to the set 1, 2 up to n such that f of x is equal to f dash of x for x is not equal to b. Means for every element other than the b, we are defining that f of x is equal to f dash of x. Means the image of x under f and f dash is same if x is other than b, and image of b under the mapping f is n. F of b is equal to n. Then definitely this f is the order preserving bijection from set A to the set 1, 2 up to n, and therefore it is the order preserving bijection, and therefore every non-empty finite ordered set has the order type of a section 1, 2 up to n of Z plus, and therefore it is well ordered. So like such we have proved this theorem 10.1. Now next one is the well ordering theorem. So the statement of the well ordering theorem is, if A is a set, then there exists an order relation on A that is well ordering. Statement is, if A is a set, then there exists an order relation on set A that is a well ordering. So this is the statement of well ordering theorem. Its proof is not in our syllabus. So let us move to the next one, corollary based on this. So the corollary based on the well ordering theorem is, there exists an uncountable well ordered set. There exists an uncountable well ordered set. Next one is the definition. Let X be a well ordered set and alpha belongs to X. Let S alpha denote the set. S alpha is equal to, it is a set of all X such that X belongs to X and X is less than alpha. Then this set S alpha is called the section of X by alpha. This set S alpha is called the section of X by alpha. Let us consider one example of this for the understanding purpose. Let us consider that capital X is the set of positive integers. Let X is equal to set of positive integers, means Z plus, and let us suppose that alpha is equal to, for instance, alpha is equal to suppose 5. Okay, then the set S alpha, will be equal to the set S 5, and this will be the set which consists of all the elements from the set capital X. Capital X means the Z plus set, means all the positive integers, such that that element should be less than alpha means 5. So which means that this consists of the set 1, 2, 3 and 4, because these are the only elements from the set X which are less than the 5. So like such we have the set S alpha. Next one is the lemma 10.2. So statement of this lemma is, there exists a well ordered set capital A having a largest element omega such that the section S omega of A by omega is uncountable, but every other section of A is countable. I will repeat once again. There exists a well ordered set A having a largest element omega such that the section S omega of A by omega is uncountable, but every other section of A is countable. Now let us prove this lemma 10.2. So for proving this lemma, we'll consider a set B which is well ordered but uncountable. So let capital B be a uncountable well ordered set, and let capital C be the well ordered set which is the Cartesian product of set 1, 2 with the set capital B in the dictionary order. Then as 1 of 1, 2 this set is countable but the set capital B is uncountable. Therefore their Cartesian product in the dictionary order will be obviously uncountable. So then some section of C is uncountable. Then some section C of C is uncountable. Next, so that which is that section which is uncountable? The section of C by any element of the form 2 cross B will be uncountable. Next, let omega be the smallest element of C for which the section C by omega is uncountable. Then let A consist of this section along with the element omega, and then this proves that section A is countable. So omega, then the section A S omega of A by omega is uncountable, but the remaining each and every section will be countable. So like such is the lemma 10.2. Now after the lemma 10.2, we have the next one, lemma 10.3. And lemma 10.3 is, if A is countable subset of S omega. If A is countable subset of S omega, then A has an upper bound in S omega. We will prove this theorem. Proof of this theorem is, let capital A be a countable subset of S omega. Then for each A belongs to A, the section S A is countable. As A is a countable subset of S omega, therefore for each A belongs to A, the section S A will be countable. Next, therefore the union B, which is equal to the union of S A over A belongs to A, is also countable, because in that case this is the countable union of countable sets. And as we have seen in the earlier article that the countable union of countable sets is union. So therefore as B is a countable union of countable sets, therefore B is countable. Next, now since S omega is uncountable, therefore the set B is not all of S omega, as we have supposed that S omega is uncountable and B is countable, therefore S omega cannot be equal to B. Next, let small x be a point of S omega that is not in B. Okay, let S omega contains the point small x and that x is not contained in B. Then x is an upper bound for the set A. Next, if x is less than A, then for some A in A, then x belongs to S A, and hence also it belongs to the set B, as B was the union of all the sets of the form S A, and which will be contrary to our choice of that element x. So therefore this shows that if we consider A as a countable subset of S omega, then A has the upper bound in S omega. So here that upper bound which we have considered is the x. So x is the upper bound of the set A which is in the set S omega. So like such we have proved this theorem 10.3 also. So today we have completed this article which was the well ordered sets. So with this article it completes our first chapter which is about the set theory and logic. And in the next article we'll begin the chapter number 2 which is about the topological spaces. Thank you.